Guys, today no handouts. We're just going to tidy up what we were doing last week and have a look at hopefully have a look at what you're required to do with the SolidWorks simulation for task 3, and then once I'm finished with that, then you're on your own. You've got the rest of the year so next week and a week after to get your analysis and your software stuff done, hopefully for this assignment to be handed in on the last week in, I think that's the last Wednesday in January. I think that's what it is. Yeah, alright. So, last week we looked at some experimental data similar to what you've got for your assignment, and we managed to derive a function that would fit that data, and it's shown in function form and graphically on the board. So we plotted those red dots from the data, and then we worked out that we could fit a sine function, and that was the best fit function that we came up with. Okay, now what we also did was looked, because the assignment is focusing on the first 20 seconds of that data and how much energy there is. So we're looking for the area under that curve between 0 and 20. And so we looked at how we could use autograph to do Simpson's rule and the trapezoidal rule and vary the number of iterations to see. Now I've just put that on there. That's the Simpson's rule version, and it's indicating the approximate area under that curve of 14.75. Yeah. Now the task also requires you to mathematically integrate that function between the limits 0 and 20. Yeah, and I ain't taught you how to do that yet. So there we go. Okay. Now, the method required for that, which is integration by algebraic substitution, is also required possibly for questions in the exam. So, although this assignment stuff's not in the exam, this method is. So we'll be going back over the first session back after Christmas in February. We'll be going through more formally this algebraic substitution. We're going to do this example question this morning, go through it step by step, and then you can apply that same method to the function that you get. And the data is quite similar, so you're more likely to get to decide on either a cosine or a sine function, and therefore the method will be similar. That's yeah, the function is kilowatts. Now we're integrating it. If we integrate that, we find the area under there, which is joules, or kilojoules. Yeah, but the function is y is equal to 1.37 sine 0.17x plus pi plus 1.53 kilowatts, because they're the units of the data. Yeah. When we're integrated, the units will be joules. Yeah. Because watts are equal to function of x there inside another function. It's like a function of a function, but we're not differentiating here, we're integrating. What we need to use is algebraic substitution. So, if you want to integrate that, can separate it into two integrals. The integral of this part and the integral of constant at the end. And we can take both sides. So first thing we would do is 1.37, this is the area, 1.37 times the integral between 0 and 20 of sine x by brackets x plus the integral between 0 and 20 of the constant on the end, which is 1.53 x. Remember when we integrate functions that are added together, we integrate the same. And I've taken the constant multiple outside of the sine function. Okay, actually what we can write this as, better than that, we can say that's 1.53 times the integral of 1 dx. So what we're going to do now is solve this bit. Yeah. So we're going to solve the integral. We're going to solve 1.37. Oh, nicely over here, Michael. Times the integral between 0 and 20 of sine 0.17 x plus pi dx. We can easily solve that other bit at the end. We're going to look at solving it. What we do is we say let u equal the bit in the brackets. Okay? And then we differentiate. So we need to find the x. What happens when we differentiate 0.17x? The x disappears. What happens when we differentiate a constant? It disappears. Yeah. And then we want this to be dx is equal to. So how do we get dx on its own here? Well, dx would come up that side, and that would go under contact. Yeah. So we can say dx is equal to du by 0.17. All right? All following so far? We can now say, therefore, 1.37 times the integral between 0 and 20 of this bit sine 0.17x plus pi dx is equal to 1.37, keep the constant, between 0 and 20 of sine u times du over 0.17. Okay with that? Or not? This is a constant. We could write that constant as, we could say, write that bit as 1 over 0.17 du. What can we do with constants? Take them outside the integral. Yeah. So that's equal to 1.37 over 0.17 times the integral between 0 and 20 of sine u du. Can someone just do 1.37 over 0.17 for me, please? .09 then we'll go with, yeah. .06. Okay. Right. So then, in your table of integrals, what's the integral of sine u? Because we're going to now integrate this between 0 and 20. So it's going to be 8.06 times something in that bracket between 0 and 20. So what happens when we integrate a sine function in your table of integrals? Yeah, so that's minus, because a here is 1 in it, so yeah, so it's minus cos u. Yep. What we now need to do is replace u with what we called u in the first place. 0.17x plus pi. So we got 8.06 minus cos 0.17x plus pi not 20. So now we've got a function, we've got our say equal to 8.06 times all of, open one set of brackets, minus cos 0.17 times 20 plus pi minus cos 0 plus pi. Close that brackets, close the big brackets. Yeah. So let's get the calculator out and evaluate.